Hey guys, another chapter 5 problem here. So I'm going to skip over problems from 5.3 for now because they are not related to the rest of the material in chapter 5. They'll show up later in the book though, as being relevant. But I'm going to go straight to section 5.4 and go over a slightly more complicated problem than last time. This is 5.2, problem 527. I'm going to share my whiteboard right now. You won't need the book because I write everything down here. But basically, the crux of this problem is getting used to some of the equations that show up for damped oscillator systems. So the statement of the problem is pretty simple. There are two things that they want you to prove. One is to prove that a critically damped oscillator can't pass through the origin more than one time. And when they say the origin, they really mean x is equal to 0. And the second thing is to do the same, but for overdamped. Cool. So I'll give a little bit of a review and a translation of what this problem is actually asking. So the translation is this. In very simple terms, x is a function of t. At various times, x is going to take on different values. And so what they're really asking for is x of t is equal to 0 for how many values of t. And so if there's only one or no values of t in which x is equal to 0, then we have proven the case that we want to prove for critically damped or overdamped systems. Just as a review, there's 3 types of damping, and so I'm not including no damping in this classification. So the 3 types of damping are weak. And so as in your textbook, this is beta is less than W naught. I will define what all these things mean in a second. Critical, beta is equal to W naught. And then overdamped. This is beta greater than W naught. Where these show up is that the differential equation, so the equations of motion for a just for a damped system is x double dot plus 2 beta x dot plus omega naught squared x is equal to 0. And so again, the dots denote time derivatives. So there are 3 different types of damping because there's 3 different types of behaviors that you get for the solution to the differential equation for this. So normally what you're going to get is the following, which is x of t is equal to e to the minus beta t times some constant, we'll call it c1, e to the mu times t plus c2 e to the minus mu times t. Here, mu is just shorthand for the square root of beta squared minus omega squared. To point out the conceptual bit here, you can see that depending on the size of omega compared to beta, the square root is either going to be real valued, imaginary valued, or equal to 0. So this differential equation is, the solution to it is valid if you have no damping, weak damping, or over damping. The solution is slightly different for critical damping because there are 2 solutions to the differential equation, but you have a degenerate solution. And so the critical damping solution is actually x of t is equal to e to the minus beta times c1 plus t c2. Again, critical damping is when beta is equal to omega, so that lambda is going to be equal to 0. So you only end up with one decaying exponential. So this is good setup for actually doing the proof. What we want to show is that x of t is at most going to be equal to 0 for only one t. What that translates to and how to solve this problem is figure out what is the t in which this is equal to 0. And we're only dealing with finite values of t, so this doesn't matter. Because the only time that e to the minus beta t is equal to 0 is when t goes to infinity. And so that's not a finite value of t. So the real thing we care about is the stuff that's multiplying this exponentially decaying bit to the solution of x of t. So that's c1 plus t c2. This is a linear equation. Linear equations have at most one 0, and you can solve for what the 0 is pretty simply. Set x of t equal to 0, divide up by the exponential, so get rid of the e to the minus beta t, and you'll end up with t is equal to negative c1 over c2. That is when x of t is equal to 0. Now, what you cannot conclude is that there is absolutely one time in which x of t is equal to 0, and I'll tell you why. This system depends on when you actually start the evolution, at which time. So if I started the evolution at some time which was greater than minus c1 over c2, we would never go through a 0. If instead I had started the evolution before then you're definitely going to go through a 0, and it's equal to the one that we solve for here. So that's critically damped. How about overdamped? So for overdamped, like I said, x of t is going to be slightly different. It's going to have that lambda factor, which is equal to square root beta squared minus omega squared. Because in an overdamped system, beta is greater than omega, we know that lambda is going to be real. So we have exponential decay and exponential growth. I can rewrite this as follows. E to the minus beta minus lambda t times c1 plus c2 e to the minus 2 lambda t. Figuring out which t we get a 0 for x is exactly the same work as we did before. This exponential bit, depending on the relative sign between beta and lambda, is going to be 0 as t goes to plus or minus infinity. One of them. So we can basically, if we set this equal to 0, we can ignore this factor. It's not at some finite time going to give us a 0. We can divide out by it, and we're left with c1 plus c2 times e to the minus 2 lambda t is set equal to 0. And so we can separate the time piece from the constant piece, and we get the following condition. Now, what we want to argue is that this equation can only be satisfied for one value of t. It's pretty easy to do that. So one way that you can justify this is that this function is a monotonic function of t. In this case, that means it's always going to be decreasing. So you can either have monotonic increasing or monotonic decreasing. You're never going to have this function gain like some hump in the middle of going to bigger and bigger values of t. A more transparent, less opaque version of this is to actually solve the equation for t. T is going to be equal to minus 1 over 2 lambda log of minus c1 over c2. So depending on the sign of c1 and c2, this again at most is going to have one time at which this can be satisfied. So if minus c1 over c2 is positive, then there actually is a solution to this equation. And again, depending on which time we pick to start the evolution, we may or may not actually go through this time to see that x gets a 0. And, if the sign of minus c1 over c2 is negative, then there just won't be a solution. So again, the nuts and bolts of the problem are actually pretty straightforward once you know how to translate it into the appropriate language. Cool. So I'm going to create a few more videos related to chapter 5 material, getting into some of the more complicated bits that come on later. And then next week, we'll also get into some problems related to chapter 6 on Lagrangian mechanics. So looking forward to it.